So hello everyone, this is lecture 45 for the mathematical physics. In the last lecture we were discussing about the non-isolated singular point. We already discussed the isolated singular points and the essential singularity. Okay, so let's take one more example. If fz equal to 1 upon z cube minus z4, then it can written like 1 upon z3, 1 upon 1 minus z. Now what are the singular points? At z equal to 0 and z equal to 1 are the singular points. And if I ask you the order, then how you can find? For z equal to 0, if you put the limit terms, then you need to multiply with z to the power 3. So n is 3 here, so it will be power of order 3. And for this one, you will multiply with z minus 1. So that will be order of 1. So it will be a simple pole for z equal to 1, and it will be for pole of order 3 for the z equal to 0. Now today we will discuss about the removable singularity or the non-essential one. Means these are the kind of singularity which can be removed from the function, okay, easily, and we will get something fz for that point. So that is why it is calling the removable singularity, because we are getting something fz at that point. So a function fz has removable singularity at z equal to z0 if fz is not analytic at z equal to z0, but can be made analytic by assigning a suitable value of fz0. So see, at z0 the function is not analytic, but still we can get something value at f, means at z0. So that is why we are calling it removable singularity. So let's take an example. Fz equal to sin z by z. So you know this, if z is equal to 0, then you will get the value equal to 1. But z equal to 0 is a non-analytic point, but still you are getting the value of this function as 1. So that is why it is calling the removable singularity. So how you can remove? So you see, just expand the sin z, z minus z cube by 3 factorial, z 5 factorial, and multiply this 1 upon z inside. So you will get this series. Now after seeing this series, you can see that if z equal to 0, then this value will be 1. So that's how you remove the singularity, and that's why z equal to 0 is a removable singularity. Let's take one more example. If here it is z minus 1, then at z equal to 1, this is a singular point, but still we can expand this in the form of series as we did in the last example, this one. And here in place of z we will get z minus 1. So again at z equal to 1 we will get again 1 only. So that's why z equal to 1 is a removable singularity in this fz. Okay, so I hope you get the point what is removable singularity and how we can remove this. So now today we will see that if we need to check that if at z equal to infinity the function is having singular points or not, or the singularity we need to check at z equal to infinity. How can we do that? How we can do the check on z equal to infinity? So fz is given, something fz is given, and we need to check if it is singular or not at z equal to infinity. Then we will assume first z equal to 1 upon t. If you assume z equal to 1 upon t, then you will get a fz in the terms of t. So that and that function we call as gt. So gt is nothing but f inside wherever you are having z, you will place 1 upon t, and that's the function you will get. It is a function of t, so it will gt. Now if z equal to 1 upon t, so we need to check at z equal to infinity, so t will be 0. So now we will just check gt function at t equal to 0 if it is singular or not. So if gt function is singular at t equal to 0, then we will say that our fz is singular at z equal to infinity. And if gt is not singular at the t equal to 0, then we will say that our fz is not singular at z equal to infinity. So that's how you can check. Let's see some example. Fz equal to 1 upon z square, we will put z equal to 1 upon t, so you will get t square here, so it will be gt equal to t square. Now we need to check at t equal to 0. So this function is analytic at t equal to 0, we know that. So we will say that this fz is analytic at z equal to infinity. Okay, so that's how you can directly check. Now if this is analytic, then it will have zeros. So what order of 0 it have? So you know how to find from the formula I have given you. So you will use 0, means at t equal to 0 it will give you 0. Then you will take the g dash, so it will give you 2t. Again it will be 0 at t equal to 0, but the second order derivative will give you 2 only. So this is your first non-zero term. So this is a 0 of second order. So t equal to 0 is a 0 of order 2, and fz at z equal to infinity has 0 of order 2. So whatever result you will get for this gt, you will apply the same result for this, but at z equal to infinity. Okay, so that's how it is working. Means it is simple, like at z equal to infinity t will be 0, so you will check at t 0 and you will get the result for z equal to infinity. Same you can check for this fz equal to z to the power 3, so z equal to 1 upon t, so you will get gt as 1 upon t3. Now see, you need to check if at t equal to 0, so at t equal to 0 this is a singular point. And what is the order? So order you can check by t minus 0 and f limit t tends to 0, so it will give you means you need to multiply t to the power 3 to get some definite value. So that's why this is the pole of order 3. At t equal to 0 is the singular point, so we can apply this result for the z equal to infinity again. So fz equal to z cube at z equal to infinity has pole of order 3. Okay, now for fz equal to exponential z, put z equal to 1 upon t. Now you can expand this according to the Taylor series. So 1 plus 1 upon t plus 1 upon 2 factorial t square, 1 upon 3 factorial 1 upon t cube. So t equal to 0 is essential singularity because it is going to infinite. So and it is non-analytic at t equal to 0. So the result will be, means at z equal to infinity, this is the essential singularity fz. Okay, so z equal to infinity is the essential singularity for fz. So you can apply the same result for the fz at z equal to infinity. Now see, if fz is given sin z, then gt will be sin 1 upon t, then expanded sin series 1 upon t minus 1 upon 3 factorial 1 upon t cube. So again t equal to 0 is an essential singularity. So the same result for this. So at z equal to infinity, fz has the essential singularity. Now that's it for the infinity or the z equal to infinity. So today we will also see about the residue theorem. So what is the residue theorem? And it is very helpful to calculate the contour integrals. So that's why we'll calculate the residue. We will see what is residue. So Laurent expansion of a function, we know when we expand means when we do this Laurent expansion, only when we have a non-analytic point inside a contour, then we expanded the function inside that by the Laurent expansion. So fz is nothing but it is going from minus infinity to infinity, a n z minus z naught n. So this was our Laurent expansion. Now see, this will have all the terms, negative, positive, and n equal to minus 1 and all. Okay, so remember, integrate term by term using a closed contour. Now we need to integrate this thing, means this is a summation minus infinity to infinity, so we can convert it into the integration. So it will go from a minus infinity, a minus means minus 3, minus 2, minus 1, a0, a1, a2, a3. So that's why we need to integrate it one by one. Now that point at which it is non-analytic, means z naught, that point is also coming inside the contour. So that encircle z naught once in contour clockwise direction. Now see, we need to integrate this. So see, for we already proved this result, that when n equal to naught minus 1, means it is n can be any value in the negative, minus 2, minus 3, minus 4. It can be positive 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, anything. So this is Cauchy integral theorem you can apply, and it will be 0 for this. But we already find it that for n equal to minus 1 particularly, for only minus 1 particularly, you will get the integral, this integral, as 2 pi iota. So if you don't know this, then just see the previous lecture, you will get it, why I am writing here 2 pi iota. So when you integrate the terms one by one, then only this term will give you something, all terms will be 0. So that's why this your integral of this complete integral of this function fz can be written in the form of 2 pi iota a minus 1. So we call this a minus 1 as the residue. Okay, so if you know the residue for a particular function, means from the expansion, then you can write the complete contour integral for that function. Okay, so that is the very essential result, means fz dz in the complete contour integral will be equal to 2 pi iota a minus 1. This is nothing but residue. So that is a very useful result which we use with the help of residue. Now we will see that how to find this a minus 1. Okay, only then we can calculate the integral. So to calculate integral, you just need the residue, then you can find it directly. So and it is simple thing, means in the integration when you have, then you know that from the Cauchy integral theorem, it is 0 for all points, but only when it includes the non-analytic point, then you will get something value. So only for this kind of terms you will get something. So that's why this is easy formula. So let's see how to find this residue. This is nothing but coefficient of z minus z naught minus 1. From here we can see this is nothing but a minus 1 is the coefficient of, in the Laurent expansion we see it is a coefficient of z1 z0 to the minus 1. So wherever you are getting 1 upon z something in the series, so the coefficient of that z will give you the residue. So and it is the coefficient of z1 z0 minus 1 in Laurent expansion, Laurent series, and it is called as residue of fz at z is equal to z0. Now if you have n number of non-analytic points, then you will have n residue inside that. So for a single non-analytic point you will get single residue, for two non-analytic point you will get two residue. So let's see residue theorem what says. So integral of fz dz, if it includes n number of non-analytic points. So if you, let's say you have 3 non-analytic points inside this contour, then integral of this fz along this contour will be 2 pi iota and sum of all the residue at these points. Okay, if you are having a single, then it will be a single residue. If you are 3, then you will the sum of the 3 residues at all points. Okay, so you need to find the residue at z1 z2 z3, and this the sum of residue will be here, and 2 pi iota will give you the complete integration. So this is your residue theorem, and fz should be non-analytic at z1 z2 z3. Okay. Now this is the residue theorem. Now we will see how to find residue for different kind of functions. So if fz has simple pole at z equal to z0, so you know what is the meaning of simple pole. It means you need to you know how to find the simple pole, that is for the singularity z minus z0 only one power. The n here will give you the pole. So it is simple pole, that means here it is only 1. So a minus 1 is nothing but limit z tends to z0, z minus z0 fz. So fz is given and z0 is a non-analytic point, so residue will be this. So remember this formula, very important. Just apply this and you will get the residue. Second, if fz has pole of order n at z equal to z0. Now this is not one order, this is of n order. Okay, so how you will do that? Then residue will be 1 upon n minus 1 factorial, limit z tends to z0, z0 is your non-analytic point. Then differentiation of order n minus 1. So if it is of n order, then it will be n minus 1, z minus z0 n fz. Now see, this formula is just a result of this formula. If n equal to 1, then what you will get? It will get you here, you will get 1, 0 factorial 1. Here it will give you z minus z0, n will be 1 and fz. So simply you will get this formula again. So remember this formula, this is applicable for all. You know how to find pole. I already told you in the previous many examples. Now if fz is given something in the form of two functions gz by hz, where gz and hz are analytic functions, these both are analytic functions, and at the z0 at which it is this fz is non-analytic, gz0 is not 0 but hz0 is 0. Okay, but h dash z0 is non-zero. So first order derivative of z0 at h is non-zero, but hz0 is 0 and this is not 0. Then what will the residue? Then fz has a simple pole at z equal to z0, means it will be a simple pole. Now residue will be same formula we will apply here, z minus z0, and this is our fz. So complete fz we will write here. So see, it is z minus z0 because it is simple pole. Now hz, now you are getting a condition of 0 by 0 here. You need to solve the limit, and at z equal to z0 it will be 0. At z equal to z0 this will be 0. So you will find the derivative. So derivative of this will give you 1, and derivative of this will give you h dash z0. So the result will be, means residue will be g z0 divided by h dash z0. So that's how you can find the residue for this kind of function, means where you have the g by hz form. So this will be your residue, this g z0 divided by h dash z0. You know what is z0? Z0 is the point where the function is non-analytic. Now you can find the sometimes you need to just write the Laurent series and you need to find the residue directly from the series. So I already told you at where you will be getting z minus z0 minus 1 power, then in the series the coefficient will give you the residue. So sometimes you need to find directly because this differentiation will be too long because of the high order. So you just apply directly, means find the series and check wherever 1 upon z you are getting, then coefficient will give you your residue. So these are the methods. Now let's see some examples where we apply these methods. So function is 1 upon z square minus 1. So at z equal to, let's find the singular points first. So z equal to plus minus 1 will be your singular points. So you can write them like this: 1 upon z plus 1, z minus 1. So z equal to, let's see for z equal to, z not equal to 1. So you know the formula. Residue will be limit z tends to z naught, that is 1 here. Z minus z naught, that is 1 here. Again z plus 1, z minus 1. So this will cancel out and z equal to 1 will give you 1 upon 2 as your residue. So first we are only seeing that how to find the residue. Then we will see how to find the integral. So first you need to find the residue only. So for z not equal to minus 1, so it will be limit z tends to minus 1. Z minus minus 1 will give you z plus 1. And fz, this will cancel out. For z equal to minus 1, you will get minus 1 upon 2. So this will be your residue at minus 1. This will be your residue at 1. Okay. Now if question given like this, 1 upon z square plus a square. So what are the singular points? Singular points are those at which this denominator is 0. So put it equal to minus a square. So z will be plus minus iota a. So these are the singular points. Let's find the residue at these points. So you can write this function as z plus iota a square, z minus iota a square. Now for z equal to plus iota a. Now it is of pole of order 2. So how you will do that? So you will use this formula. For pole of order n, it will be n minus 1 factorial. So it will be 2 minus 1 factorial here. 2 minus 1 factorial, and here it will be d by dz z minus ia, and differentiation is the order of n minus 1, so it will be 2 minus 1 1, and here you will get 2 and 2, it will cancel out, these two terms will cancel out. Then simple differentiation and put z equal to iota a, so you will get this value 1 upon 4 iota a cube. So this will be your residue at plus iota a. Now similarly you can solve for minus iota a, you will get your residue as minus 1 upon 4 iota a cube. Now let's see one more thing. Fz equal to sin z over z4. Now see, if you find the pole, then it will be of order 3, pole of order 3. So you need to find the, if you use this formula, then you need to find the second order derivative, and it will be little bit complex. So what you will do, you will just write the Lorentz series. So sin z will be z minus z cube by 3 factorial plus z5 by 5 factorial and so on. So multiply this 1 upon z4 inside. So you will get 1 upon z cube and minus 1 upon 3 factorial 1 upon z. So in the series, what is z minus 1 is here. So coefficient will give you your residue. So minus 1 upon 3 factorial is your residue. Now you use the formula we already discussed. So it is of pole of order 3. So n minus 1, 3 minus 1, and differentiation will be 3 minus 1, 2. And here you will get z minus z naught. And you will solve this, you will again get the same value, minus 1 upon 3 factorial. Okay. So that's how you can verify that both are same. So let's see one more example. Fz equal to z exponential 1 upon z. So simply expand this exponential 1 upon z according to the Lorentz series. So 1 plus 1 upon z plus 1 upon 2 factorial z square plus 1 upon 3 factorial 1 upon z cube plus and so on. Multiply z inside. So z plus 1 upon 2 factorial. So this is z minus 1. So 1 upon 2 factorial will be your residue. Now this is your last example for today. Fz equal to tan z. So tan z can be written as sin z by cos z. So let's find the singular points. For cos z equal to 0, z will be plus minus pi by 2, plus minus 3 pi by 2, and so on. So now you are having infinite singular points. So let's say we need to find residue for z not equal to pi by 2 only. So see, you can write this function as this is gz over hz. And you can see that g at z naught pi by 2. Gz is not 0, but hz is 0. Hz naught is 0. And if you find the h dash z naught is not 0. So this satisfies the last condition we already discussed. This one. So we can just apply it directly for residue. Gz naught divided by h dash z naught. So find the h dash. So h dash z naught will be minus sin pi by 2. It is just like cos z will give you minus sin z. So minus sin z is your h dash z. So at z naught it will be minus sin pi by 2, and gz naught will be sin pi by 2. So it will give you minus 1. So your residue at z naught equal to pi by 2 will be minus 1. So that's all for today. In next lecture we will see some more example to find the residue. Then we will see how to find the contour integral using the help of residue. Then we will, in the last lecture, in the completely last lecture of this complex analysis, we will see about the branch point singularity, where we are having the z to the power fractions, okay, means fractional powers of z, and then you are having some singularity. So these are called the branch point singularity. So we'll see about them also. So that's it for today. Thank you everyone.